Hello all, I'm excited to have you at the second part of the GOB series lecture. Today, we'll be talking about the review of critical topics that are important to the continuation of the second part of this GOB class. You know, the first part we looked at normal physical and inorganic chemistry. In this part, we'll be looking at the organic chemistry part and then the biochemistry part of this class. And it's important for us to make a connection to important topics, to critical topics that will make us to be successful in this class. And that's exactly what we're going to be doing. But before we do that, as usual, for some of you who have followed the trail of my class, I usually start with a quote. In this case, I'm starting with a quote of a chemist. He said, "We define chemistry as a chemistry of carbon compound." Augustin Kekule came up with this quote when he discovered the structure of benzene, you know, the resonance structure of benzene. And I put a little bit of something here. I said, challenges ahead. So this class might be challenging. You have a lot of content, but I want to tell you this is that, what I want to say is this, is that you shouldn't be discouraged. You are capable of doing it. Others have done it. So you're going to be doing it well. So I'm wishing you success and luck as you undertake this venture. Let's take it off from there and look at our learning goals. What are the things I'm going to be covering in this lecture? This lecture, like I said, is just a review of those topics we did earlier in the first part of this series. Now, these are the topics that you've been used to already, and I had a lot of other external sources in Canvas in which we're going to look them up in details if that need to be. However, it's going to be going up. I'm going to be taking a look at them really very quickly and not just very in-depth, but this is going to be a very good foundation if in any case you've forgotten what you did in the last part of this class. So what are we going to be looking at? We're going to look at bonding in this class, particularly like covalent bonds. And I'm also going to be talking a little bit about ionic bonds, although we will not be talking about ionic bonds here, but it's important I bring them in looking at how atoms interact with each other as to form molecules and compounds. And we'll look at how to draw Lewis structures. In fact, Lewis structures actually mean structural formulas. The real structural formulas that we'll be doing in this class is just the Lewis structure. But this time, we'll draw the word Lewis structure and say structural formulas. And then we'll know how to draw the short form of Lewis structure, which we call the condensed versus the expanded structural formula, expanded or extended. And then we'll know how to draw what we call the line angle structures, where we use only lines to represent structures of molecules, and how to also make them open them up as extended structures. Then we'll look at the old folk, we look at the VSEPR model. The VSEPR model, where we look at the structure of the atoms, the lone pairs, the bonding, and even its polarity as well. And then we also look at oxidation and reduction in terms of oxygen and hydrogen. So these are the things I'm going to be covering as we move on. Let's take it off from there immediately. What is a covalent bond? So we're going to be looking at covalent versus ionic bond. You see, covalent bonds are formed when it's, okay, let me just be general first. Bonds are formed between atoms when atoms interact to form compounds and molecules. That is when atoms form bonds. And the reason why they want to do this is that atoms want to maintain stability. Now, the stability of atoms are maintained when they form this bond to achieve the octet rule. Remember that again? The octet rule. The ability of atoms to achieve 8 electrons in their atomose shell. That is a level of stability that is inherently owned by the noble gases. Every atom wants to look like noble gases, and hence they want to go into these interactions between one another to get like this guy. Now, there are two types of bonds, the covalent bond and the ionic bond. Covalent bond is what we're going to be doing in this class. Organic compounds are mainly covalent bonds, although there are derivatives we're going to be talking about that are ionic, but the majority of them are covalent bonds. Now, these covalent bonds are formed when atoms do what? Share electrons between one another. Now, the sharing may not be perfect. The sharing may not be perfect. The sharing can be perfect at times. When the sharing is completely perfect, we'll say that such a bonding is called a. Now, like I said, the pure covalent bonds are when these atoms share electrons completely equal with one another. Now, polar covalent bond is when the sharing is not equal. And however, it occurs between two. This sharing of electrons must occur between a non-metal and a non-metal, or a non-metal and a metalloid. Now, and then ionic bonding involves just the transfer of electrons from one another. Transfer of electrons. One atom loses an electron which is gained by another one. In such a relationship, they form ionic compounds, and the bond that hold them together become strong ionic bonds. Now, but let's see what happens. I'm going to use a common example here, methane, the formation of methane. That's what I'm going to use. Now, if you look at your periodic table, let's look at the periodic table. Now, hydrogen is in group 1, carbon is in group 4. So what that tells us is that hydrogen is in group 1, we have one electron in its atom. So if you look at the periodic table, like again, as you see that, let's go look at it, it's in group 1. So this is hydrogen, and this is carbon. So what it means is that carbon has carbon has 6 electrons, in total of 6 electrons, while hydrogen has what? 1 electron in the atom. So what does that tell us? Now, if we're going to be writing the Lewis symbol, we're still going to talk about this. The Lewis symbol is a symbol used for atom, used to write when atoms do what? To write atoms and show the only electrons in its atmosphere. Remember again, like we did in the last part of this class, that in Lewis symbol representation, we're not interested in the inner electrons. Our only interest is in the electrons in the atmosphere. So the number of electrons in the atmosphere in hydrogen is going to be 1 because it's in group 1. Remember, the group number represents what? The group number represents what? The number of electrons in the atmosphere. So this is group 1, this is group 4. Remember, this is 4, IV, this is group 1. So writing the Lewis symbol, let's see. So it's going to be hydrogen is in group 1, it's going to be 1 dot in the atmosphere. Plus, if it is reacting, if it's forming a bond with carbon, carbon is in group 4. What it means is that carbon is going to have 1, 2, 3, 4 electrons in the atmosphere. We're not interested in the core electrons because the core electrons does not go into bonding. The core electrons in carbon is 2 electrons, which is inside the inner shell. We're not interested. We're interested in what happens at the atmosphere. Now, if carbon wants to become like what? It wants to be 8. Remember, every other element apart from hydrogen is going to want to become 8. Hydrogen will be 2 because it has a small nucleus. But the rest will become an octet. That means they want to become 8. What it means is that carbon is going to gain 4 electrons to become 8 here, whereas hydrogen is going to gain 1. So when they come together, they can share this bond. What is going to happen? 4 of this hydrogen atom will come together with 1 atom of this to share this bond. What is going to happen? Remember again, each of these guys will have 1 electron in the atmosphere. Here, or the total number of electrons here is 1 electron. Here, carbon has 6 electrons. Inside that 6 electrons, 4 of them is in the atmosphere. And here, this one has only 1 electron. That 1 electron is its atmosphere. Now, when they come together and share this bond, what happens to them? Look at what happens here. Now, carbon, I'm going to use a different color, okay, to make this even much better. I'm going to try to remove this and use green. Now, I'm going to use green for this to tell you that they want to share this bond. Good. So if I go back here, I'm not going to have carbon. Let me draw my carbon again. Now remember again, carbon is coming into this relationship with what? 4 electrons already in the atmosphere. Hydrogen has 1 electron, but we have 4 hydrogen. So look at what is going to happen now. One of these hydrogen will give 1 to this one. Will give 1 to this. Give 1 to this. And give 1 to this. To form this interaction. What is going to happen? There will be a hydrogen here. 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 Forming, okay, I'm going to use a different color now. Forming this bond. This is what we call the sharing of these 2 electrons between each of these hydrogen and carbon is what we call a covalent bond. Now look at what is happening here. Now, in this relationship, carbon brings 1 electron, hydrogen brings 1 electron. The relationship is equal. And no one is to share. Now, what is happening now? At the end of the day, how many electrons will carbon have at this point? Now, carbon has 4 plus another 4 it gains from 4 of this. So carbon now has what? 8 electrons obeying the octet rule and becoming stable. Whereas each of these hydrogen will now have what? Two electrons. Let me use a different color. We have 2 electrons here now. 2 electrons, 2 electrons, and 2 electrons, because it wants to have 2 to be stable. So this particular molecule, this is a methane molecule, is much more stable than the individual atoms of carbon and hydrogen. And if we want to draw this in the real sense, the way we draw it in the typical structural formula, Lewis structure is going to be, remember, every covalent bond just simply means a pair of electrons. Hydrogen is sharing an electron with this, sharing an electron with this, sharing an electron with this, sharing. So each of these represent two pairs of electrons, as you have just seen. So this is what we call, these 2 pairs of electrons is what we call a covalent bond. So this is how covalent bonds are formed. What about ionic bond again? Like I said, I'm just going to I'm going to use two familiar folds to do this. Sodium and chlorine to form common salt. Now sodium is in group what? Let's look at it. I'm going to just write sodium plus chloride first. And then let's go back to that, my periodic table. Sodium is in group 1 again. So now it's going to have 1 electron in the outermost shell. Chlorine is in group 7. This is group 7, VIIA. It's in group 7. So it's going to have 7 electrons in the outermost shell. If we go back there again, the Lewis structure or symbol of sodium is going to be this. And that of chlorine is going to be, okay, no, I'm going to use a different color. I want to use a different color for that. I'm going to use green here. And here I'm going to use 7 electrons. So I'm going to put 2 here. I'm going to put 2, 4, 6. I'm going to put 7 here. Now what is going to happen? This involves transfer, whereby a metal loses its electron to a non-metal. That's what is happening. So carbon is going to lose this electron to this guy. Now carbon, like I said, has 11 electrons in the neutral state. This has 11, let's write it down. It has 11 electrons. Inside that 11 electrons, it has 1 electron in the outermost shell. That's exactly what it has. 11 electrons, 11 protons. Here has 17 electrons, 17 protons. Now, the actual configuration of sodium here is that sodium has 1 electron. So assuming I want to write a shortcut, it's going to be, okay, no, I'm going to put it here. It's going to be 281. I don't have enough space for that, but I'm going to find a place to fit it in. So here, sodium it has 2 electrons in the first inner shell, another 8 in the second shell, and 1 in the outermost shell. So I'm going to just put 1. That's the one we are seeing at this point. What about chlorine? Chlorine has 2, 8, 7. This 7 is what you see in this outermost shell. So I'm going to just put this thing here. So this is the outermost shell. So what is going to happen? The moment sodium loses this 1 electron, it will only form an ion that has only 8 electrons. Whereas chlorine is not going to form an ion that has another 8 electrons by gaining 1. So what happens in the next drawing will be sodium is going to form an ion that has a positive charge. Now remember, it has lost one of those electrons. That electron is not going to now gain by chlorine. Remember, chlorine has this already. And this. One of those sodium electrons will now be taken by chlorine. And what happens? Chlorine is not going to assume a negative sign. Look at what is happening here now. Remember, this one just lost this one electron. So the new configuration of sodium ion is going to be 2,8. It now has 8 electrons in its outermost shell. Whereas the new configuration of chloride ion is going to be 2, 8 plus 8, because it gained 1 to become 8. So the outermost electron here is 8, the outermost electron here is 8, and both of them are now stable. And they will now assume, the sodium will assume a positive sign, so this one will assume a negative sign. How does it assume this? Look at what it assumes. If you want to calculate the sign like you did in your previous class, the number of protons minus the number of electrons. Here, it has 11 electrons. Here, it has 10 electrons. So 11 electrons minus here is 10 electrons. 11 electrons minus 10 electrons will give you 1 electron. That's why we put a plus here. Here now, again, we say the proton minus electron. Sorry, that's what you say. You just say proton, 11 proton minus the electrons here. So the same thing we're going to do here. So here it is what? Here it is 17. 17 minus 18 will give you minus 1. 17 minus 18, here it is 18, is going to give you negative 1 electron. So it has an excess of electron. Here, there is a deficiency of 1 electron. Here, there is an excess of 1 electron. So this is how these bonds are formed. And then we go to the next thing we want to talk about. Covalent bonds again, just to finish them up. Now, we can use the periodic table to indicate, to predict the number of bonds that can be formed by element. And that's exactly what we're going to do. We're going to deal with the common element. Now, from what I did so far, you would have seen the example. I did that of carbon and hydrogen. Now, for non-metals, particularly because they are the ones that form covalent bonds, non-metals and metalloids, the number of bonds formed is equivalent to the group number minus, 8 minus the group number. If you want to make it a shortcut, just say, okay, that group number, if you get the 8 minus the group number tells you the number of bonds that will be formed by that atom. Or you can say the number of what? Electrons that it will share. That's exactly what you're going to say. The number of electrons that it will gain. How many electrons will it gain to form the octet group, to become the octet group? Carbon is in group 4. Okay, let's start from example. Carbon is in group 4. So let's just put the symbol C. Now, for it to form 8, since it's in group 4, for it to form 8, it's going to gain what? It has 4 electrons in the atom shell. So it has to gain 4. That is why you find it in group 4. So the Lewis symbol is going to be like I did earlier, 4 electrons in the atom shell, because the Lewis symbol only shows you the number of electrons in the atom shell of that atom. So how many bonds is it going to form? For it to form 8, it has to gain extra 4 bonds, extra 8 electrons to become octet. Or you can say 8 minus 4, so it's going to form always 4 bonds. That's the number of bonds to become a neutral atom. Oxygen is in group 6. Let's look at it. Oxygen is in group 6. Vi is in group 6. So it's going to be 8 minus 6 is going to give us 2. So the Lewis symbol, of course, is going to be 6 electrons. So we're going to, first of all, put 4, then 5, and 6. So these 2, 4, 6. So if you say 8 minus 6, it's going to form, that's what oxygen forms, only 2 bonds in the neutral atom. What about nitrogen? Nitrogen is in group 5. 5A. So it's going to have 5 electrons in the atom shell. It's going to say this, and another one here, 5. So how many bonds is it going to form? It's going to be 8 minus 5. It's going to form 3 bonds in a neutral atom. What about sulfur? Sulfur is in group C, like oxygen. So it's going to be the same thing. Sulfur is still in this group. Well, this oxygen group 6 is here. So it's going to form the same thing. So 6. So it's going to be 8 minus 6. It's going to give us what? 2. What about chlorine? Chlorine is in group 7. So 8 minus 7 is going to give you 1. That's why chlorine and all the halogens form 1 single bond and 3 lone pairs. So chlorine, if you write the Lewis structure, it's going to be 1, 2, 3, 4, 5, 6, 7. It's only remaining 1. So it's going to be, it just needs only 1 to get to form. That's why it forms 1 bond. Or you say 8 minus 7, it's going to form only 1 bond. What about hydrogen? Hydrogen is in group 1. Now, remember, hydrogen is an outliner in the periodic table. This does not concern hydrogen at all. It's an exception. So just know that hydrogen is in group 1. It will only what? It only forms 1 single bond, 1 single pair of electrons. So the Lewis structure is this. So it only gains 1 electron to become 2. So that we're not going to be using the 8 minus. We're going to just say that it only gains, because it gains only 1 electron to form 2 electrons that it needs. Therefore, it only forms 1 single bond. So in drawing the Lewis structures, we're not going to be drawing the Lewis structures like you did in the last class, which is okay. You can still use that method. But in this method, we're going to be predicting the number of bonds that are formed by this, and we're going to use that to draw the Lewis structure. You find out that you're going to be saving a tremendous amount of time, instead of first of all beginning to count the atomos electrons and then begin to distribute them as we did in the last class. So it's important you memorize this number of bonds that can be formed by these classes of atoms in the periodic table. And now we go to the next thing. Say drawing the Lewis structure. Now, Remember the rules for drawing the Lewis structure. I'm going to try to draw a few of them, first of all, within the same rules that we applied, that you used. The first rule is what? We're going to count the number of electrons in the valence shell. So let's count. Carbon is in group 4. It has 4 electrons in the atmosphere. Plus hydrogen is in group 1, but it has 4 atoms. So we're going to say 4 times 1. If 4 times 1 is 4, 4 plus 4 gives us 8 electrons in the atmosphere. That's the first step. The second step, you distribute the atoms around the central atom. Now, hydrogen can never be central atom. Therefore, it is our carbon here. So you distribute them with a lone pair of with a pair of electrons around the carbon. Carbon is always at the central atom. And then you now see if your atoms are distributed. Let's see. Remember, one single bond is 1 electron. 2 bonds is 2 pairs of electrons, which is 4 electrons. 3 bonds is 3 pairs of electrons, which is 6 bonds. So this is 2 electrons. 2, 4, 6, 8. We have 8 electrons satisfied. So we don't need to do any other thing. This represents the Lewis structure. Now, this tells you this. Remember what we did in the last page. Hydrogen will always form 1 bond. Carbon will always form 4 bonds. If you look at it, carbon is just forming 4 bonds. And these 4 bonds can be single bond. It can be double bond. Now, so what does that tell you? So in drawing that of hydrocyanic acid, HCl now. So what are we going to see? Whenever you see carbon, carbon is always at the center. And I try to write this formula to tell you that. So I'm going to see hydrogen will be here, carbon will be here, nitrogen will be here. I don't want to count the electrons because that's the trick I'm going to show you here. Now remember, here now, carbon always forms 4 bonds, right? Hydrogen will only form 1 bond. So you cannot even add anything here. It's going to make this thing wrong. But you can add something between these two. So what does that tell you? Now, how many bonds in a neutral atom? The number of bonds that is always formed by nitrogen is what? It's 3. So having known that, and carbon can also form 3 bonds, I can put another bond here. I can put another bond here. So here now, nitrogen forms 1, 2, 3 bonds between carbon. And carbon can also take it. So the total number of bonds formed by carbon now becomes 1, 2, 3, 4, which is okay for carbon. And nitrogen forms 1, 2, 3, which is okay for nitrogen. But we're not done. We have to make sure that each of them satisfies the octet rule. Hydrogen is already satisfied with 1 bond. Carbon is satisfied 2, 4, 6, 8. What about nitrogen? Nitrogen has 2, 4, 6. How are we going to complete it? You have to add a lone pair at this side. So this now becomes, nitrogen now has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Hydrogen has this. So if we want to confirm this, how do we confirm it? Let's confirm it. Hydrogen is in group 1 plus, carbon is in group 4, 4. Nitrogen is in group 5, 5. This will give us 10 electrons. Let's calculate the total number of electrons here to see if it corresponds to this. Let's count. 2, 4, 6, 8, 10. That tells us that this Lewis structure is very correct. So you see, this is beautiful. Knowing this pattern will make you draw the Lewis structures really very fast. The same thing we go with the next one we're going to do. Okay, let's look at the next one. To draw the Lewis structure of this, carbon, like I told you, forms 4 bonds. It can be in 2, it can be in 3, it can be in 1, depending. So it's going to be at the center here. We're going to distribute these ones around it. It's going to always be at the center. Now, remember what we said. Iodine is in group 7. Every group 7 element will always form what? If you say 8 minus 7, it's going to they form 1 bond. So they already formed the number of bonds they need. They don't have to form any other bond. What you're going to do now is to complete the lone pairs on these atoms to make them to be 8. If I complete the lone pairs, because they already formed their 1 bond. So, but we're not done. Now, carbon still is not satisfied here. And the bond you have here is between these guys, right? So carbon has 1, 2, 3. It's remaining 1. It has to form 4 bonds. And you cannot, if you put a lone pair here now, this oxygen will be marginalized. So what do? You put a single bond here. If you put this bond there, what happens to carbon? Carbon is not satisfied. 2, 4, 6, 8 electron. Then these ones are satisfied. Now what happens to this oxygen? Remember, oxygen forms 2 bonds because 8 minus 6 is 2. So what do? You use lone pair to complete it. That is how you draw the Lewis structure. The same thing will happen with these two. Carbon is always at the center. For carbon dioxide, if you put carbon here, okay, I'm already preempting myself. I shouldn't do that. If you put this, you put this. What do you do next? Carbon will always form 2 bonds. Carbon will form 4 bonds. Oxygen will form 2 bonds. So it has to form 2 bonds here and 2 bonds for oxygen to make it correct. And in doing that, carbon now has 4 bonds. It's satisfied. What do you do to oxygen? You put the lone pairs. You put the lone pairs here and here, here and here. And this becomes the Lewis structure of carbon dioxide. Because you are forming it based on the predicted number of bonds that it makes in a neutral atom. That is what you are using, instead of counting the electrons. We go to the next concept. So in this case now, instead of saying using the word drawing Lewis structure, I'm not going to use the word again. I'm going to be saying drawing structural formula, because structural formula is still Lewis structure. But in this case, we're talking of organic molecules. Now, in drawing this Lewis structure, particularly when it involves what? When it involves carbon. Now, remember, carbon will always have 4 bonds. I tell you this. It can be in 2, it can be in 3. It doesn't matter. It can be in 1, provided it is. And it's always at the central atom. So let's see this one now. Here now, this is CH3. This tells us that this hydrogen is attached to this carbon. So that's exactly what it tells us in organic compounds. So if I draw this now, I'm going to say this is all attached to the carbon. So I've gotten this. So what it means, the remaining 1 chloride will be attached here. Chloride forms only 1 bond. What it means is that every group 7 forms 1 bond. It must have 3 lone pairs. So you have to complete the lone pairs. And this is the structural formula for this. What about this one? Again, this has 2 carbon. The 2 carbon is going to be at the center. Hydrogen, as usual, is going to be away. Now, here, carbon is not satisfied. It's not satisfied at all. So what are you going to do? But hydrogen is satisfied. So you don't care hydrogen against 1. How do you satisfy carbon? Just add 1 bond here. And this becomes the Lewis structure of this molecule. And you can confirm that by counting the number. If you count the number of electrons here, this is 4 times 2 plus 2 bracket 1. 4 times 2 is 8. 8 plus 2 is 10. If you count 2, 4, 6, 8. No? What did I do wrong? 4 times 2 is 8. Yeah, 4 times 2 is 8. 8 plus 2 is 10. So let's count 2, 4, 6, 8. Yeah, I'm missing something. 2, 4, 6, 8, 10, 12. What am I missing? I'm missing something at this point. So carbon is in group 4. It does have. Oh my God. Okay, I'm missing out something here. There's a little bit of mix up. Okay, thank God I observed that. Please, this is C2H2. This is C2H2. So we're not done. You see, if you look at this molecule, we are missing something. We did something wrong. Good. It's good that I picked this up immediately. If you look at this molecule, something is wrong here. What is wrong? I have 4 hydrogens here. 2 hydrogens, I have 4 hydrogens. This is wrong. So what I'm going to do, I'm going to take it off again. It's good I observed this. Good job. So if you look at this now, this happens to a lot of students. A lot. Now, whereby then I have 2 hydrogens, I put 4 hydrogens. Where did I get it from? This is wrong. I'm going to take it off. So I'm going to, just to make it easy, I'm going to take everything off and do what? Start afresh. Good job that I got this. So now, like I said, it is always good for you to count your electrons. So here we have 4 times 2. 4 times 2 gives us 8. 8 plus 2 gives you 10 electrons. That makes sense. That's exactly what I have at this point. So if I want to draw this now, I'm going to have I'm going to have only 2 hydrogens attached at this point. Now, if you look at this, carbon itself now is not satisfied. It forms 4 bonds, but here it has only, from here it has 2, here it has 2. What is going to happen? I'm going to add 1 here. If you add 1 here, it's not still satisfied. It still has 2, 4, 6. 2, 4, 6 is not. So I'm going to add another bond. If you add another bond, it is now satisfied. Oh no, that bond is too far. So I'm going to add it here. So you now have, this have 2, 4, 6, 8. This one have 2, 4, 6, 8. So it is forming, this is actually called ethane gas or acetylene. That is exactly what it's formed. So this is the correct Lewis structure of this molecule. And let's count the number of electrons again to prove that. It is always good to count the number of electrons. That is how I figured out that I made a mistake here. So this is 2, 4, 6, 8, 10. That is correct. We did it. This is what we need to do at this point. Because we don't have that other thing. The other molecule I draw was ethene gas. And that is not what I was supposed to do. That is very good. Now let's get to this one now. The next one again, using the same way, if carbon is going to form the central atoms here, that's exactly what it's going to form. Wait, I'm going to come back to it. So there are 4 of them. And we have 6 hydrogens. So I'm going to put this one here. This is satisfied. So we have how many remaining? And then I'm going to put the other one here. It's always good to try to put the hydrogens first at the outermost atom, because hydrogens is better being there, because it just gains 1 pair of electrons. So what are we going to do next? What do we do next? What I'm going to do next is to make sure that we have how many hydrogens again? So let's count. We have 6 of them. So we're not done. We can distribute more. Now, we can put it, if you put it here, let's see what happens. If you put it here, 6, 6, carbon is not satisfied, right? So what are we going to do? If you put a double bond here, you see this carbon now has excess. This is wrong. What are you going to do? You go back. So, okay, this is wrong. We're going to remove it. So you're going to remove it. So what do? I'm going to put that hydrogen here. If I put it here now, this carbon has 3. This one has 3. This is satisfied. You need to have 4 bonds. So what I'm going to do? I'm going to put a double bond. If you put a double bond here, this now has 2, 4, 6, 8. 2, 4, 6, 8. They're all satisfied. And the number of hydrogen we have is 6. 1, 2, 3, 4, 5, 6. And this is correct. So here now, this one has single bonds. That's why I illustrated. This has triple bond, and this has double bond. So if you want to draw the Lewis structure of the last one, which is water, we draw this all the time. So again, hydrogen can never be central. So we're going to have something like this. What does that tell you? Oxygen is always forming 2 bonds, because 8 minus 6 is in group 6, forms what? 2 bonds. So that means the number of bonds you need to form is okay, and the number of bonds hydrogen needs is okay. What do you do next? Use the lone pairs to complete it to the octet rule. So that it now has 2, 4, 6, 8 to satisfy the octet rule. And this becomes the Lewis structure of water. So you can actually draw the Lewis structure without having to count the number of electrons. And that is exactly what you're going to be doing in this class. Now, to take that a little bit further, we'll be talking about the condensed versus the expanded structural formula. Now, the condensed versus the expanded structural formula. Condensed is just a shortcut, short way, short form. Whereas the expanded is what I did in the previous page, drawing every atoms out completely and showing them. That's what we mean by expanded. So this molecule shows you the condensed structural formula. So I want to write it in an expanded form and open it up. So this is expanded. Now look, listen, there is important things we need to know. We do this all the time in organic chemistry using this. Whenever you see CH3, CH3 simply means a single carbon. This is actually a methyl group. We're going to talk about that much later. This is called, this is CH3. If you look at this CH3, then when you see CH2, CH2 simply means this is CH2. So, and if you we saw this here. So what are we going to do? So first one is CH3. We're going to represent that. So CH3, we're going to put it here. So it's going to be C. You have CH2, which is this. You put the CH2. Here's another CH3. You put it at this point. This becomes the expanded structural formula of this molecule. Let's do that of this. Now, we have CH3 here. First of all, let's situate it. CH3 will give us C. We have oxygen. Now, this oxygen is attached to another CH3. And of course, oxygen forms 2 bonds and having 2 lone pairs. Now, in this class, you will not be required to always be putting the lone pairs. After like this review class, I won't expect you to be putting it again. So, but I just want to show you how that is used to predict the number of bonds that are formed by this atom. If you look at this again, let's do this one. To write the expanded structural formula, you have CH3 like I told you here. So you're going to have this. We situated that. Now, here you're going to have OH. OH is a functional group. You just write it as OH. So you can say O to combine to H. Again, oxygen is always having what? 2 bonds, which makes it okay. Carbon has its normal 4 bonds. You can put your lone pairs. Always have 2 bonds and 2 lone pairs. Let's do this one. This one has nitrogen again. Remember what I said about nitrogen? Nitrogen always have what? 3 bonds and 1 lone pair. Let's see. We have CH3 here first. Let's put it. CH3 is this. we have CH2, we put it there. And then the last one we have NH2. NH2 means nitrogen attached to 2 hydrogen. Nitrogen is always having 3 bonds and 1 lone pair. So you can always put your lone pair at this point. So this is how you draw the extended structural formula from the shortcut. These are what we call the shortcut. These are the shortcut or the condensed. This is the condensed form of this formula. And we've written the expanded structure. This is very, very important because in most of the structural formulas I'll be doing as we get deeper into this course, I can present them either as expanded or condensed, or I can mix up the two. It does not matter. The most important thing is for you to understand that. Then we now take that a little bit further. We've looked at the condensed. We looked at the expanded. What about what we call the line angle structure? Line angle structure simply is a way of representing organic compound using just lines and angles. So what does that simply mean? We use a line. A single line represents the simplest single line represents an ethane. So what it means is that each line, each dot represents a carbon. And if you put it in a line, it is connected to another carbon. So what that simply means, and now, anytime you have 2 lines meet together at the vertex, like if you have a line meet to another line, it forms an angle. You know, this is an angle, and that's why we call it line angle. So what are we going to do? So now, remember, there's important caveat here. You see, all other atoms must be represented. The only atoms that are not represented in line angle formula is what? Is carbon and hydrogen. Carbon and hydrogen is not shown, but every other atom is shown. And if that atom has a hydrogen on it, it must be shown. But for carbon, we don't need to. Let's start. Now here, we're going to start with this. This has 2 carbons. So we're going to say, this is the first carbon, this is the second carbon. This is the shortcut of this molecule. So this is CH3, another CH3 here. So this is a single line. So this is, let me count. This is 1, 2. This is 1, 2. That is how we present this molecule in condensed structural form. Okay, let's look at this one. Now, let's look at this one. Now, if you look at this one now, this one has, the best thing I test, always try to count your carbon, not to be confused. So this is 1, 2, 3, 4. Nitrogen is attached at this carbon number 2. Let's see how that goes. Now, we're going to start it this way. So, you have to draw it as a line and angle. If you draw it as a straight line at times, it will confuse you. So I'm going to start by drawing the first one as 1, 2. So this is my first carbon, this is my second carbon. Then this is my third carbon. So this is now my 1, 2, and 3 carbon. But I have another carbon here. What do I do? Let's see. I'm going to put it here. So this will be the 4th carbon. So this will be my 4th carbon. But I'm not done. What about my nitrogen? My nitrogen is attached at this point. What am I going to do? I'm going to put it at this point and put my nitrogen. Now remember this. Every hydrogen on any other atom must be shown. This nitrogen has 2 hydrogens on it. It must be shown because it is not carbon. If it is carbon, you don't have to show it. So look at that of carbon here. This carbon has 3 hydrogens, is not shown. This one has 3 hydrogens, is not shown. This one has 3 hydrogens, not shown. But every other molecule must have it shown. Does that make sense? Now, you feel free to pause this video and try out other ones before you come back to them. So let's look at this one. If I look at the next one, for this one, let's see what happens. Now, this is what we call cyclic compounds. We'll talk about them. Now, so the first thing you need to do again, you draw this one like a polygon. A polygon. A polygon is a shape that has more than 4 sides. You remember that. We do it in your rudimentary mathematics. So let's see what happens here. So now, you're not going to show the carbon. I'm going to put it this way. This will look like a pentagon. This is actually a pentagon. The carbons are not shown. The hydrogens are not shown. However, we have other atoms that are not this. So what it means, the number of bonds must be shown. You have to always show the number of bonds. If it is 1 single bond, you have to show it 2 or 3. So you show this oxygen here. It doesn't have a hydrogen. We don't need to worry. But it has another one connected to this point that has a hydrogen. So you have to show it. So this becomes the skeletal formula for this cyclic molecule. Let me put it that way. I don't want to name it for now so that not to confuse you. because this has two functional groups. Now let's get to the next one. Now, like I said, you have to always show the number of bonds. The number of bonds are not affected. That's what I'm going to illustrate with this one. But first, I'm going to count the longest chain. Let me count the longest chain. The longest bond will be 1, 2, 3, 4, 5, 6. And then it's 7. So this 7 is acting as an attachment. So I'm going to try to situate it. I'm going to start. Remember, anytime you have a single bond, this thing is going to bend. It's going to change shape a little bit. That's what it shows. But we're going to see that much later. But I want to show you how this is done. Now, I'm going to start from, you can start from anywhere. If I start from this, okay, let me start from this side. I have this connected to this here. And then I have this one. Now, this is connected to this. This has a triple bond. So there's a carbon here, there's a carbon here. That's what it shows. Carbon, anytime you have a triple bond, the molecule does not bend, because triple bonds, like we did in the first part of this series, makes molecule linear. You're going to see this in your first lab. That's why this molecule is linear at this point. So it makes this, and then we have, so now we have, after this, we have this one here, and then what I'm going to bend this one now, and this is the last one. So let me count my number of the longest chain first. Remember, I have 6 here. So I'm going to say 1, 2, 3, 4, 5, 6. That is correct. So I have 1, 2, 3, 4, 5, 6. I have 1, 2. The double bond is between 1 and 2. And then the triple bond is between 2 and 3, you have single bond. Between 3 and 4, you have the triple bond. Between 5 and you have this attachment. So this is how you represent this molecule in what? In skeletal formula. In skeletal formula, you have to show all the bonds, whether it is double, triple bonds. And like I said again, like in the one we have here and the one we have here, you have to show all the atoms. Apart from hydrogen and carbon. That is how we draw the line angle formula. So we have another example that does the same. Now we're going to work it backwards. Say convert the following line angle to extended. You can say extended formulas or extended structural formula or expanded structural formula or structural formula. Anyone I say is okay. Now, so let's do that. Remember what I told you? Here means CH3. There's CH3 here. Here will be 2 hydrogens here. And here will be another CH3. That's what it means. So if you're going to draw this now, I have 1, 2, 3 carbons. So I'm going to say, I'm going to have this one here. I'm going to have 2 here. And I'm going to have another 3 here. This is the expanded. If I want to do the shortcut too, remember, the shortcut is going to be CH3. This is CH2. And this is another CH3. So I can even take it to the extended. I can take it to the condensed. It doesn't matter. Now, let me go to this one. Going to this one again. Again, this is like another pentagon. So I'm going to try to put all the carbons. Remember, there's a carbon here. There's a carbon here. If I put all the carbons, oh, okay. No, I got that one. I want to change what I have in here. Okay, good job. So this is what I have. So now listen, carbon will have to satisfy the octet rule. You have to put this one that is here already. Now each of these carbon have to satisfy the octet rule with hydrogen, because that's what is missing. So you start putting your hydrogen, 2 hydrogens here, 2 hydrogen here, 2 hydrogen here, 2 hydrogen here, and 2 hydrogen here. That is what you got. This becomes the full structural form. Okay, let's do this one. For this one again, now remember, like I said again, all the bonds must be shown. All the double bonds must be shown. Now we have a double bond here. We have a double bond here. And we have oxygen here. We'll now try to make sure that carbon has all the hydrogen in it. Here the carbon has 4, is okay here. So here it has 2, so I have to put 2 hydrogens here. Here it has 1, 2, 3, 4. It needs 1 hydrogen here. Here it needs 1 hydrogen here. Here now it needs 1 hydrogen. Here it needs 1 hydrogen to be 4 bond. And this is the extended formula for this molecule. What about this one? Let's do this one. Remember, here is going to be CH3 here. It's going to be CH3. Here there is 4 bonds. That means there's going to be 1 hydrogen here. And then here now there's going to be CH3 here. So let's do that. So if you count the longest chain, let's count the long chain. 1, 2. We can start with this one. So there is the chain here is just about 1, 2. So I'm going to say 1, 2. And this is connected to a nitrogen. And then remember, this one has another hydrogen connected. That's a CH2. So we'll put this here. Now you see here now has 1, 2, 3, 4 bonds. It only has one hydrogen. That's why I put it here already. And then this nitrogen has another bond connected to it, another carbon. And this carbon must, anytime you see this carbon, this is a carbon, it has CH3. And then this nitrogen has a hydrogen at this point. So this is the full or extended structural formula of these molecules listed. So you can easily play around with converting from the line angle to the extended, or the extended from the extended to the line angle. And doing this practice, particularly with the worksheet, is going to help a lot. Now, the VSEPR model. Let's talk about the VSEPR model a little bit. The VSEPR model, remember when we talked about the VSEPR model? The VSEPR model tells you about the what? The VSEPR model tells you about the shapes of this molecule in terms of their molecular geometry and the electron geometry. Remember, the electron geometry is the number of electrons, including bonds, surrounding the atom. Whereas the molecular geometry is the way the atom looks. Now, there are 3 molecular geometry that we'll be looking at, which is when an atom has 4 things attached to it. When it has 4 things attached to it, the atom usually becomes tetrahedral. When it has, this atom has 1, 2, 3 atoms around it. So it's going to become what? Trigonal planar. Here, this atom, each of these one, like this carbon, has 2 atoms attached to it. This one has 2 atoms. In this case, we have what? Linear configuration. Now, the bond angle here, when 4 things are attached, is 109.5 degrees. Here is usually 120 degrees, and here it is usually 180 degrees. Now, like you said, like I told you, whenever you have a double bond, the molecule becomes linear. That's why the structure we saw we drew earlier, the one we drew earlier, that is why the structure looks this way. Because the double bond, the triple bond will make it linear, will make it a linear molecule. And the bond angle will be 180 degrees. Now, so what do we need to know? These are those things we're going to be seeing. Now, at times, in some other molecules, you will see this, you see lone pair getting involved. I'm not going to go into those now, but we're going to see them as it moves. So these are our main primary focus in this class, particularly as it relates to carbon. Because carbon, organic chemistry, we're going to talk about this much later, is basically the study of carbon and its related compound. So the example here, this molecule actually is a 10. So this is C2H6. This is C. Oh, I missed it. This is C2H4. And this is C2H2. And these are the 3 classes of hydrocarbons that we'll be talking about much later in this class. So once again, just try to remember again that what's the importance of this VSEPR model? The importance of this VSEPR model is going to change the molecule, and changing the shape of a molecule can determine its polarity or not. That is going to take us into other things we're going to be doing. So it says fill in the lone pairs and the bond angles in this molecule. So when you are confronted with this kind of problem, the first thing you need to do is to redraw the molecule and make sure that each of these atoms has its lone pair. That's what I'm going to do. I'm going to try to draw it completely open structure. So let's start. If I draw this thing open, you don't have to bend it. If you want to bend it, that's fine. But I want to draw it in a linear structure. If I'm going to draw this in a linear structure, start with this. So this is methyl group attached at this point. This has a nitrogen. This nitrogen also has this. Now, this is connected to 2 hydrogens. And this is connected to this. And then this again is connected to this. So let's check what we did. We have this here, correct? We have this here. We have this. We have this. We have this. Now, it says fill in the lone pairs and the bond angle. That's what we want to do. So now let's see if atoms obeys the octet rule. So make sure that all atoms must obey the octet Let's see if that is happening in what we've just done. I'm going to use a different color. Here, carbon has four bonds, which is supposed to form. 4 bonds means 8 electrons, satisfied. Here it has 4 bonds. So we don't worry, all the carbons are satisfied. So let's go to nitrogen. Nitrogen has 2, 4, 6. It's not satisfied. It must have to take 2 lone pairs. Remember what I told you about nitrogen? Nitrogen forms 3 bonds and 1 lone pair. Here again, carbon forms 2 bonds. No, oxygen forms 2 bonds. That means it needs 2 lone pairs to complete it. Every other one is okay. Every other carbon is satisfied because it has 4 electrons. This one has 2, 4, 6, 8. 8 electrons of 4 bonds around it. So every other one is satisfied. So within that having said, we want to determine what? Around each of these atoms, we want to determine their bond angles. Now this carbon is surrounded by 4 atoms. When you have 4 atoms around it, the bond angle is going to be 109.5. So it's going to be 109.5 degrees. What about this nitrogen? This nitrogen is surrounded by 3 bonds and 1 lone pair. So there are 4 attachments around this nitrogen. Because there are 4 attachments, it's still going to be 109.5 degrees. This carbon has 4. It's still going to be 109.5 degrees. What about this one? Okay, let's see this one. This one has how many things are around this carbon? It has 1, 2, 3. Remember, in VSEPR model, you count double bond as 1. So there are 4 atoms attached to this. This is 1, 2, 3. Therefore, the bond angle here, when 3 things are attached, remember, will be 120 degrees. And what about this one? This carbon has 1, 2, 3, 4 things attached around it. This is also going to be 109.5 degrees. So this is how you determine you determine the bond angles of each atom. Okay, we've not done this one. This carbon 2 has 1, 2, 3, 4 things around it, 109.5 degrees. The truth of the matter is this, is that when carbon is completely satisfied, particularly with single bonds, individual single bond, the bond angle is going to be 109.5. When it has double bond, it's going to be 120. When it has triple bond, it's going to be 180 degrees. And that exactly is what it is in the VSEPR model. Now, again, let's move to the next one. It says, let's talk about the formal charges. Now, formal charges is the charge an atom has on its own. The charge an atom is carrying on its own in a molecule. Now, when the atom has the adequate number of bonds it's supposed to form, the formal charge is 0. You don't even need to worry about it that much. But once it exceeds that, you're going to calculate the formal charge. And the formula to calculate formal charge is the valence electron. That means the number of electrons in the atomic shell minus the sum of the dots. The dots are the number of electrons plus the bond. We're going to see how that plays out. So it says indicate the bond angles, the lone pairs and formal charges in all atoms, except hydrogen, in all these molecules here. So you must complete the lone pairs. So first of all, in doing the formal charge and the bond angle like we did in the previous slide, you have to complete the what? You must have to do what? Complete the formal charges. Sorry, the lone pairs. So let's start from there. Hydrogen is always having 1 bond, so it's okay. Nitrogen is supposed to have 3 bonds, but here it has 4 bonds, but it's okay. But how many? Is it satisfied at the octet through 2, 4, 6? It's satisfied. So since we're good, everything is satisfied here. What are we going to do? Let's calculate the formal charge on nitrogen. The formula is nitrogen is in group 5. Remember, I showed you that earlier in the periodic table. Feel free to always use your periodic table by the side and confirm that. So the formal charge is going to be 5 electrons, which is the minus the number of bonds. It does not have any dot, no lone pair, no dot. But it does have bond. How many bonds? 4. 5 minus what? 4. 5 minus 4 will give us what? 1 plus 1. So the charge on this is plus 1. And then the bond angle here, because it's surrounded by 4 atoms, it is what? 109.5 degrees. 109.5 degrees. That's how we do this. So remember, we do every atom except hydrogen, so we don't need to bother about hydrogen. Let's go to this one. Let's talk about the atoms here. So we're going to do that of carbon, oxygen, and bromine. Let's do that of bromine. Let's start from bromine. Bromine is not satisfied, so we have to make it satisfied. Bromine is in group 7, forms one bond, and has 3 lone pairs. So we're going to put 3 lone pairs here. So how do we do the formal charge? To do the formal charge, now what do? The formal charge here is going to be, it has bromine is in group 7, right? So for bromine, it's going to be 7 minus, how many dots does it have? It has 2, 4, 6 dots plus 1 bond. 6 plus 1 is 7. 7 minus 7 is 0. So no need, whenever it is 0, no need to add it because it's neutral. So here, bromine has the number of lone pairs and the number of bonds it's supposed to form. So we're not going to do anything on it. We're not going to put anything. It's going to remain that way. What about carbon? See, carbon forms 1, 2, 3, 4. Anytime carbon forms 4 bonds, it's neutral. So, but you can always do that yourself. Let's see, carbon here forms 4 bonds. So what it means is the valence electron, carbon is in group 4. 4 minus, group 4 is 4, minus, how many bonds does it have? 1, 2, 3, 4, it has 4 bonds, no lone pair. So 4 minus 4 is 0. So you don't need to bother. Carbon is, so this carbon here and this carbon here is 0. You don't even need to work on the other one again. So let's go to the next one. Oxygen is what we're going to bother about. This oxygen has only 1 bond. And it's abnormal. It's also supposed to have 2 bonds. But since we don't see that, what do? We use lone pair to complete. To make it 8, this is 2. We have to put 3 lone pairs here. So now it has 2, 4, 6, 8. It's satisfied. If we try to calculate, let's see if we can calculate what it has here. Let's calculate its formal charge. So calculate its formal charge on this oxygen is going to be, now oxygen is in group 6. It will be 6 minus, how many lone pairs does it have here? It has, how many dots? 6 dots. Plus, it has 1 bond. So 6 plus 1 is 7. 6 minus 1 will give us -1. So here, this nitrogen is charged. It has a charge of -1. And again, like I said, here carbon, the charge, the bond angle will be 109. Here will be 109.5. And then what about this one? Let's go to this one. This one has nitrogen too. So I need to work out the one that has a nitrogen too. Okay, let's start with this. Let's start with, we've not done anyone with sulfur. Let's do sulfur. Sulfur is in group 6 with oxygen. Sorry, with oxygen, yes. So what it means is that it needs 2 bonds and 2 lone pairs to complete the octet rules. So this 2, 4, 6, 8. Now, let me give you a secret. Anytime a bond has the number of, anytime an atom forms the actual number of bonds and lone pairs, it will be neutral. But let's do that. So sulfur is going to be group what? Is in group 6. So it has this, is in group, okay. Let's get this thing clear. Now, sulfur is in group 6 like oxygen, right? And what it means is it has this electron in its valence shell. So it will be 6 minus what? 6 minus, how many dots does it have? 4 dots. Plus, how many bonds? 2. 4 plus 2 is 6. 6 minus 6 is 0. So it's 0, I told you. So it's going to be 0. The same thing with oxygen here. If you see this oxygen, it's going to be 0 because it has 2 bonds and now you're going to complete it with 2 lone pairs. So if you do it here, it's going to be 6 minus 4 plus 2 again. This will give you 0. So this is okay. It is 0. What about this nitrogen? The same with this nitrogen. Nitrogen is supposed to form 3 bonds and 1 lone pair. If we satisfy it here, if we want to calculate it, so it's going to be, it's in group 5. 5 minus 2 dots plus 3 bonds. 2 plus 3 is 5. 5 minus 5 is 0. So this is it. So since we saw that everything here is neutral, yes, I purposely did this, everything is neutral. And then to determine the bond angle, this has 4 attachment, 4 bonds. So this is 109.5. Here, this has 1, 2, 3. Because of this double bond, it's going to be 120 degrees. Because there are 3 things attached to this carbon. There is 1, 2, and 3 attached to it. And then what about this one? This nitrogen has 4 things attached. It has 1, 2, 3. And a lone pair. The lone pair makes it 4. So therefore, here is going to be 109.5 degrees. So this will be the bond angle of this. This is the bond angle. All right. So this is how we work on the formal charge of molecules. And having said that, we've come to the end of this lecture. Now, in the second part of our review, we'll be looking at the polarity of molecules and oxidation and reduction. Thank you for listening and do have a wonderful day. Bye.